The smartest AI on your phone was trained by a dumber one. That model in your pocket, the one that answers questions, writes messages, translates languages, it has about 1 to 3 billion parameters. That's tiny. The best AI models have hundreds of billions. And yet this tiny model is shockingly good. A 1.5 billion parameter model recently scored 73% on a competitive math exam. That's better than GPT-4o. A model 400 times smaller, beating one of the most powerful AI systems ever built. How? It didn't learn from better training data. It didn't have some clever architecture trick. It was taught by a bigger model. Specifically, a massive model with hundreds of billions of parameters was trained first, the normal way. Then that big model's knowledge was compressed, distilled into the tiny one. The small model didn't learn from textbooks. It learned from its teacher. This is called knowledge distillation, and it's the reason AI works on your phone at all. The technique goes back to a 2015 paper by Geoffrey Hinton, and the core idea is surprisingly simple. But to understand why it works so well, you need to see what normal training misses. When you train a model the normal way, you give it labels. This image is a cat. This one is a dog. These labels are called hard labels because each one picks exactly one category. 100% cat, 0% everything else. The model learns to match these labels and it gets good at classification, but here's the thing. Those hard labels throw away a ton of information. Think about it. A photo of a tabby cat isn't just a cat. It looks a little like a tiger, a little like a lynx, nothing like a truck. A trained model actually knows this. Its internal probabilities say 91% cat, 5% tiger, 3% lynx, 1% dog, practically 0% truck. Those tiny probabilities for tiger and lynx aren't noise. They're real information. The model learned that cats and tigers share stripes, fur, pointed ears. Cats and trucks share nothing. Geoffrey Hinton called this dark knowledge. It's hidden in the probability distribution, and hard labels completely ignore it. Now here's where it gets clever. There's a way to make this dark knowledge more visible. You take the model's output, the raw scores before the final probability step, and you divide them by a number called temperature. Low temperature, like 1, gives you the normal sharp distribution. 91% cat, almost 0 everything else. But crank the temperature up to, say, 20, and the distribution softens. Now it's something like 40% cat, 20% tiger, 15% lynx, 10% dog, 5% truck. The ranking stays the same, but now those relationships between classes are amplified. You can see the structure. This is the key insight. A trained model's soft probabilities contain richer information than the original training labels ever did. Not just which class is correct, but which classes are similar. Which ones share features? Which ones the model almost confused? And if you could transfer this richer signal to a smaller model, that smaller model would learn much better than if it just trained on hard labels alone. Here's how distillation actually works. First, you train a large teacher model the normal way. Big architecture, lots of data, lots of compute. This model gets really good at the task. Now you take this trained teacher and run all the training data through it again, but with high temperature. For each input, instead of just getting the predicted class, you get the full soft probability distribution. Those softened outputs become the training signal for the student. The student is a much smaller model, 10 times smaller, maybe 100. You train it with 2 goals at the same time. First, match the teacher's soft probability distribution. For every input, make your output look like the teacher's softened output. The loss function for this is called KL divergence. It directly measures how different 2 probability distributions are. Second, still get the actual answer right. You combine these 2 losses. About 90% comes from imitating the teacher, about 10% from the hard labels. That balance matters. Too much teacher signal and the student copies the teacher's mistakes. Too much hard label and you lose the dark knowledge. And it works remarkably well. the student ends up significantly better than training from scratch on the same data. A distilled student can match a teacher 10 times its size. It didn't just learn what the right answer is, it learned the landscape. Which answers are close? Which mistakes are reasonable? Which ones are absurd? All from the teacher's soft probabilities. And once the student is trained, you throw the teacher away. The student runs on its own. Smaller, faster, cheaper. That's the classic version, distilling what a model knows. But in 2025, something more ambitious happened. Researchers distilled not just knowledge, but reasoning itself. DeepSeek built R1, a massive 671 billion parameter model that learned to think step by step through pure reinforcement learning. It solves problems by writing out its reasoning, checking its work, backtracking when it hits a dead end. Think of it as the teacher who not only knows the answer, but shows all their work. Then they did something clever. They took R1 and generated 800,000 step-by-step solutions to math, logic, and coding problems. Each solution included the full reasoning chain. Not just the answer, but the thinking. Let me break this into parts. Okay, the first part gives me this. Now for the second part. Wait, that doesn't work. Let me try a different approach. They filtered these down to about 600,000 correct ones and used those as training data for much smaller models. The results are wild. A 1.5 billion parameter student trained on those reasoning chains scored 73% on the AME math competition. That's a test designed for elite high school students. GPT-4o scored lower. A model 400 times smaller, matching one of the most advanced AI systems because it inherited its teacher's way of thinking. The 7 billion parameter student was even better. The 32 billion one was nearly as good as the full 671 billion teacher. And it's not just the answers that transferred. The students write out their reasoning the same way the teacher does. They check their own work. They backtrack. They say things like, that doesn't look right. They inherited the entire reasoning process. This is a fundamentally different kind of distillation. Hinton's original version transferred what a model knows, which classes look similar, which features matter. DeepSeek's version transferred how a model thinks, the step-by-step process, the self-correction, the verification. The student didn't just get the teacher's answers, it got the teacher's mind. Distillation is usually just the first step. Once you have a smaller model, you compress it further. Quantization takes the model's weights from 32-bit numbers down to 8 bits or even 4 bits. That's a 4 to 8 times reduction in memory just from using less precise numbers. Then pruning removes the weights that barely contribute. Trim the unnecessary connections, keep the important ones. Stack all three together, distillation, then quantization, then pruning, and you can take a 671 billion parameter model and shrink it down to something that fits on a phone. The accuracy drops a little, maybe 10 to 15%, but the speed and size improvements are massive. This pipeline is why AI works on your devices right now. Meta's Llama 3.2 has 1 billion and 3 billion parameter models distilled from their 70 billion parameter teacher. Google's Gemma 3 starts at just 270 million parameters, small enough to run in 125 megabytes. Microsoft's 5.4 runs on laptops. Every one of these was distilled from a much larger model, and it's not just phones. Distilled models run in cars for real-time navigation, in robots for object recognition, in smart speakers for voice processing, in medical devices for on-the-spot analysis. Anywhere compute is limited and latency matters, distillation made it possible. The reason this works goes back to Hinton's core insight. A trained model knows more than its labels say. Its probability distributions encode relationships, similarities, and structure that hard labels completely miss. When you distill that into a smaller model, you're not just copying answers, you're transferring understanding. And with reasoning distillation, you're transferring thinking itself. The next time you use AI on your phone and it gives you a surprisingly good answer, remember, it was taught by a giant model you'll never see. The teacher did the hard work. The student inherited the knowledge. And that's why the smartest AI on your phone was trained by a dumber one.